a team of researchers from University of Toronto Engineering and Rice University have reported the first measurements of the ultra-low friction behavior of a material known as magnetene. The results point the way towards strategies for designing similar low-friction materials for use in a variety of fields, including tiny implantable devices. Magnetene is a 2D material, meaning it is composed of a single layer of atoms. In this respect, it is similar to graphene, a material that has been studied intensively for its unusual properties, including ultra-low friction, since its discovery in 2004. While graphene is made of carbon, magnetene is made from magnetite, a form of iron oxide which normally exists as a 3D lattice. The team's collaborators at Rice University treated 3D magnetite using high-frequency sound waves to carefully separate a layer consisting of only a few sheets of 2D magnetene. The University of Toronto engineering team then put the magnetene sheets into an atomic force microscope. In this device, a soft-tipped probe is dragged over the top of the magnetene sheet to measure the friction. The process is comparable to how the stylus of a record player gets dragged across the surface of a vinyl record. The bonds between the layers of magnetene are a lot stronger than they would be between a stack of graphene sheets. They don't slide past each other. What surprised the researchers was the friction between the tip of the probe and the uppermost slice of magnetene. It was just as low as it is in the graphene. Until now, scientists had attributed the low friction of graphene and other 2D materials to the theory that the sheets can slide because they are only bonded by weak forces known as van der Waals forces. But the low friction behavior of magnetene, which doesn't exhibit these forces due to its structure, suggests that something else is going on. The researcher says that when you go from a 3D material to a 2D material, a lot of unusual things start to happen due to the effects of quantum physics. Depending on what angle you cut the slice, it can be very smooth or very rough. The atoms are no longer as restricted in that dimension, so they can vibrate in different ways. And the electron structure changes too. The researchers found that all of these together affect the friction. The team confirmed the role of these quantum phenomena by comparing their experimental results to those predicted by computer simulations. The researchers constructed mathematical models based on density functional theory to simulate the behavior of the probe tip sliding over the 2D material. The models that incorporated the quantum effects were the best predictors of the experimental observations. The researcher says that the practical upshot of the team's findings is that they offer new information for scientists and engineers who wish to intensely design ultra-low friction materials. Such substances might be useful as lubricants in various small-scale applications, including implantable devices. For example, one could imagine a tiny pump that delivers a controlled amount of a given drug to a certain part of the body. Other kinds of microelectromechanical systems could harvest the energy of a beating heart to power a sensor or power a tiny robotic manipulator capable of sorting one type of cell from another in a petri dish. These scale-dependent effects, combined with the fact that iron oxide is non-toxic and inexpensive, makes magnetene very attractive for use in implantable mechanical devices.